Good afternoon. I'm Peter Fisher, head of the Office of Research, Computing, and Data, and I work in the Vice President for Research's office. And I'm former head of the physics department. And the title of this last session is Foundations of Quantum, which is vague enough so that we're just going to say anything we have to say, right? Foundations, I take to mean the irreducible ideas and rules of quantum mechanics, how we understand them now and how we might learn them in the future. As head of the physics department, and this certainly continues to this day, I always felt a strong effort in quantum information science would advance our understanding of quantum mechanics, which is really a key mission of the department. And quantum mechanics is really our best theory so far. It's actually true, I believe, that the rules of quantum mechanics, the application to the basic principles, are not terribly complex. I once told our former provost, Cindy Barnhard, that the rules of quantum mechanics are about as complicated as the rules for contract bridge. The interpretation of both is far more complicated, and this panel is going to explore deeper into what quantum mechanics can tell us about our universe. So with me today, and their names are up, we have Muji Bawendi, who's from the chemistry department, who studied the quantum properties of quantum dots, which is an almost one-dimensional quantum mechanical circuit. Professor Peter Shor, who's been mentioned several times in the math department, and of course invented the famous factoring algorithm, which is a key to cryptography, and also laid the basic foundations for quantum error correction. Professor Wolfgang Ketterle made the first observations of gas atoms condensing into a single quantum mechanical object. And finally, Professor Pablo Guerrero Herrero, who first observed a new form of superconductivity, which is the lossless electrical transmission of energy formed by a very simple system, which is just two layers of carbon atoms. Each of these discoveries, the dots, the factoring, condensing, and new superconductivity, spawned an entire field or fields of research. So these four scientists have really advanced the field of quantum mechanics enormously in the past few decades. Looking at this group, I believe that just standing here, I'm lowering the intellectual capacity on stage by about 20%. So we're going to start with about 30 minutes of panel discussion where I will pose some questions to the panel, and then we'll have some time for Q&A from the audience, and you are going to tell us the questions? Okay, I'm going to sit over here. You can still hear me? All right. Well, thank you all for coming. This is an exciting day, and we want to really kind of delve into the foundations of quantum however you want to. So I thought we'd just start with an easy question. We'll start with Pablo and go down the row, and just take a couple of minutes and explain what you think you did to open a new field and why it was important. So Pablo?
Okay, thank you very much, Peter. So it's quite simple what we did. There is this sheet of carbon atoms called graphene. It's one atom thick, and we took two of them and we placed them on top of each other at a certain angle, and this thing turned into a superconductor when neither of the two sheets is a superconductor by itself, right? So this was something which was a big surprise, was unexpected, not predicted by theory.
So wait a minute, how did you know what angle?
Oh, it's called a magic angle. That was predicted, the angle, but it wasn't predicted that it would become a superconductor. With just this magic angle, 1.1 degrees, that was predicted by theory. So theory played a role there. And then over the past 7 years, basically we've come to figure out that using this trick, which by now it's called twistronics or Moire quantum matter, we can realize pretty much all of the phases of quantum matter that exist in the universe, or at least those that appear in the solid state. And that means that this is viewed by many people as a sort of a new platform for quantum simulations, sort of in between traditional quantum materials and ultra-cold atoms in optical lattices. We have quite a bit of control, degree of control, not as much as the cold atoms, but we're able to observe many, many phases of quantum matter. And that's something which has kept people very active.
So I've heard. Professor Shore.
Yeah, so I guess in 1994, after thinking about the problem of what useful stuff could a quantum computer do for a couple of years, I discovered that a quantum computer could factor large numbers into primes. And this, this really set off a huge surge of interest, because the internet security is based on the fact that computers cannot factor large numbers into primes. So a quantum computer could break your security on the internet. And once I'd made this discovery, a bunch of people said, this is never going to work because you can't correct errors on a quantum computer, because you can't measure a quantum computer without disturbing it, and you cannot copy a quantum state, so there's no way to correct errors. So then I came up with a way to do quantum error correction, and this, really set the stage for the possibility that quantum computers could eventually be built.
What did you have in your mind as what a quantum computer looked like when you were developing these two algorithms? Or did you just think of it as a complete abstraction?
Okay, so when I first heard about quantum computers, they were described as quantum Turing machines. But a quantum Turing machine is a very complicated device, and I started talking to physicists, and they could not get their minds around quantum Turing machines. It's, it's completely impossible to build a quantum Turing machine, and I mean, they're a nice theoretical device, but physicists don't work in theory, they work in, well, I don't want to say in practice, but in terms of interactions they can actually visualize. So after talking to them, I came up with a quantum circuit model, which you have a whole bunch of qubits, which are two-state quantum systems, and you perform quantum gates by making two of them interact. So you make them interact in pairs, and then there's a very complicated list of how they interact in pairs. So first you make a, say, control NOT gate to qubit 1 and qubit 5, and then you turn qubit 5 with a 90-degree rotation, et cetera, and that is a quantum program. And this is a concept that physicists found really quite easy to understand. So what I was thinking about in terms of quantum computers evolved from quantum Turing machines to quantum circuits, but you can theoretically do the same thing with quantum Turing machines as you can do with quantum circuits. So at a higher level of abstraction, my concept of quantum computer didn't really change.
Thank you. Wolfgang.
Well, if you ask me what I did, I took a bunch of atoms and made them really cold. So it's as simple as I'm saying it. There was a field of cold atoms, and I was an assistant professor and said, why can't we get colder? What are the limits? What are the practical and theoretical limits? And you just work hard to make atoms colder and colder. There is a certain naivety, because some people said it's not useful, or what can you do with cold atoms? And I hadn't fully figured it out. I just felt here was a goal. It would enable new science. It would take the physics of interacting and colliding atom into a new regime, and getting colder was just an important frontier. Of course, when we succeeded, I there was so much more what could be done. I could not have imagined that Bose-Einstein condensate in the hands and minds of many people would be the quantum substance of, a zero entropy state, which can be formed and modified into analog quantum simulations, into models for black holes, into models for whatnot. So eventually, the mindset of pursuing it was much more focused and simpler than what people were able to make out of it. And for me, it's an example which I think also plays a role for QMIT. Quantum mechanics does not live in the abstract. Quantum mechanics needs real platforms and real systems. And I have really seen disruptive progress happening if you create a new system of twisted bilayer, if you create a new system of ultra-cold atoms, because it makes people think about the quantum mechanics in a different way. Even if people said before, well, there's nothing new. Bose-Einstein condensation is trivial. We have already superfluid helium, which is much richer, much more complicated. But so eventually, you just have to believe that even if something already exists, if you do it in a completely new system, it can change the paradigm. So for me, when people say there is a phase transition, well, it's boring because it's already in a universality class which we understand. But if you have the same phase transition in a system which is just different by its appearance and by its properties, just do it and then figure out what new things you can do.
Well, and your apparatus, I mean, you did it the hard way. He did it the easy. Your apparatus filled a room, probably two.
Mine was very small, Scotch tape.
Well, compared to what we do now, it was simple. I mean, you just take atoms, cool them down, and watch them.
Professor Buendi.
So the question that my community was asking at the time, the late 80s or so, was, what happens when you take a intrinsically quantum mechanical system like an atom, and you take a bunch of them together, and the more you take of them together, you eventually get a piece of bulk material, like a piece of wood or a piece of silicon. And those properties become very classical. And if you look at an electron in an atom, it's a quantum mechanical object. If you look at an electron in a circuit, you think of it as a particle moving around that circuit. And how do these properties emerge then from the atomic properties? How many atoms do you need to get to out of the quantum regime into? And so that was really the question, the curiosity that we were trying to answer. And in order to be able to answer those questions, we had to make really small things that were not yet the bulk material. And at the same time, that was the kind of the birth of nanoscience, because these properties emerge at the nanoscale regime. When you have hundreds or thousands of atoms together, maybe bigger than a molecule, but certainly smaller than a piece of bulk. And that was the challenge that I faced as an assistant professor coming in. My career depended on it to actually make something that was very well defined, that we could change the size and watch the properties change with size and see the emergence of classical properties. And that's what we made. We made these little quantum dots out of semiconductors. And they're called quantum dots because you put an electron in a quantum dot, and it has this beautiful quantum mechanical properties that you can then manipulate, and then you can change by doing all sorts of things to them.
One electron.
One electron in there, right? And you can put multiple electrons and they start interacting with each other. Yeah. You take quantum dots, bring them together, and you can get them to interact with each other, and it becomes a platform for doing all sorts of things. And the other thing that it allowed us to do, because these are very small and we were chemists, is to begin to understand how to interact these things with worlds that we knew about, like the biological world, and this is something that we had to work hard of how to get these inorganic materials incorporated and talking to the biological world. And this is something that's going to be very important as we move ahead and think about quantum systems, quantum sensors to detect brain waves and things like that. How do you incorporate these engineered objects that are quantum objects into the biological. It's not so trivial, but we have the beginnings of understanding how to do
You're
that.
talking about from a biological compatibility.
Compatibility, yes. I mean, the biological systems are very, first of all, they're in water. You know, we tend not to be in water. They're at room temperature. There's all sorts of things you have to worry about. But we're learning how to do that with the simple things that we call quantum dots, for instance.
So I think in some sense, all of you have created very different platforms for illustrating important aspects of quantum mechanics. And moving forward, I'm curious what you see as the really important recent advances in quantum simulations, which Feynman always thought was the low-hanging fruit of quantum information science. I do sense there's a real blurring that's starting to happen between simulation and actual computation, which is something interesting. Pablo, do you want to comment on emergent properties, for example,
Yes.
of quantum
So
mechanical systems?
I think that quantum simulations are becoming very, very interesting as they are augmenting the degree of control that they have over multi-particle systems. And I think that one area which is traditionally very hard for example, for solid-state systems, is systems out of equilibrium. So, you know, in solid-state systems, everything is interacting strongly with everything. You know, electrons, phonons, magnons, photons, everything. It's very hard to isolate and control different degrees of freedom independently. But this is something that quantum simulators are very good at. They have exquisite degree of control with, you know, via lasers over all the parameters of the system. And as a result, they are much more able to follow non-equilibrium physics of multi-particle states, you know, entangled, you know, many particles interacting with each other very precisely. And I think that that's an area which is very, you know, very ripe for discoveries, which for example, solid-state physics is, you know, it will take longer or they're too messy and it's hard to make discoveries in that area, you know, more than ground state properties, which are a little bit more manageable in solid state, for example. So I think out of equilibrium, it's turning into a very interesting area.
So, Professor Shore, do you think of, can we think of quantum error correction as an emergent property in a many-body sense, or is that pushing it too hard?
Well, so Alexei Kitaev, I think sometime in the late 1990s, figured out how to do quantum error correction by essentially simulating topological quantum materials. So that, you know, ties quantum error correction very close to quantum materials. And his theory is really beautiful. Unfortunately, you know, maybe not unfortunately, but all the people who are doing quantum error correction are not using his idea. They're using much more straightforward quantum error correcting codes, but there's really nothing that keeps, you know, you have a quantum computer and, you know, you have, you know, qubits next to each other and they talk to each other, and you can put them into this simulation of these exotic quantum topological quantum field theories, and then you can use these topological quantum field theories to do quantum error correction. And the main difficulty with doing this is you need to interact more than 2 qubits at once. But you know, we're making progress, and maybe there'll be a completely new way of doing quantum error correction that's practical using these ideas.
Okay, I think you and Pablo brought together something that I want to ask Wolfgang about, which is the idea of out of equilibrium. And you know, if you think of a circuit, I think of circuits sometimes as things that just kind of jump from one equilibrium state to another, whereas this sounds much more like biology, which is a continuous system that's continuously out of equilibrium. And I know Wolfgang has thought about this. If you remember when we taught 8033 together, we had a long discussion about exactly this. What are your thoughts on emergent properties and things that come out and go back into equilibrium as quantum computing elements?
Well, there's general interest, of course, in understanding systems out of equilibrium, because nothing would happen if systems would not go out of equilibrium. Equilibrium is kind of the entropy death of a system. So, but traditionally in physics, it is hard to study systems which are far away from equilibrium, because relaxation times of standard systems, especially solid state systems, are very, very fast. And so in my field of ultra-cold atoms, we have now the favorable situation that everything has really tremendously slowed down because we work at nano-Kelvin temperature. So, I mean, I sometimes say at nano-Kelvin temperature, the speed of sound is millimeter per second. So at nano-Kelvin temperature, it would take an hour until my voice travels to the end of this room. So this is crazy how slow the system is. And with time resolution, which is not even nanosecond, maybe microsecond or millisecond, we can study processes which would happen in solid state system on a femtosecond time scale. So we can create systems at negative temperature and study the dynamics of negative temperature systems and such.
Okay,
so I think there are many opportunities.
I think you're freaking people out when you start talking about negative temperature. Can you elaborate on that a little bit?
Well, negative temperature is, if you go to infinite temperature and you put more energy into the system, you cross over to negative temperature. So it's a misconception. Negative temperatures are more energetic than positive temperature. So you're not cooling to zero and then you go to negative temperature. You are heating up to infinite temperature and then the transition to negative temperature happens. So nothing to be freaked out.
Okay. Thank you very much. So you talked about quantum dots and how quantum dots interact with each other, and they can presumably do more than binary interactions. What emergent properties of a system of quantum dots?
So I want to pivot from your question.
Okay, you can pivot.
That's fine. Okay.
But pivot means you have to put one foot. You have to keep one foot in the same place.
Okay. So I'll stay with chemistry then.
All right.
Wolfgang just talked about how fast you go to equilibrium in physics. But in chemistry, you can actually go very slowly towards equilibrium. So in chemistry and biology, we're very lucky that we're out of equilibrium, that we can stay out of equilibrium for a long time.
Okay.
Right? Otherwise, we'd all, like you said, we'd all be dead, right? So clearly, there's something very complicated that happens when you take very large systems that are all coupled to each other and in the presence of dissipation. And I think this is something that we can go towards with quantum simulators. We can build really complicated systems that may mimic an array of quantum dots that are all talking to each other, and we don't know where it's going to go, because we may think we understand the physics of the two-body physics, but we really don't understand the many-body physics, right? And we try very hard, and the bigger the system is, and when we get to a biological system or a chemical system, they become really huge. And that's where I think the simulations are going to be able to help us to extract out novel theories to think about these huge systems. I think part of the way that simulations are going to help us is not just to show what happens, but to inform the theorists on how to think about these things in a way that's going to help us to become more intuitive about it, which we don't have right now. We don't have that intuition.
In the way we have an intuition about classical systems, yes. It comes to us from our everyday life. I mean, is this a feature of the different set of rules that quantum mechanics really has. Pablo, you had a comment?
Yes, so I wanted to add, because I think that point is very interesting. We're in a panel on the foundations of quantum, and I think that one of the key aspects in terms of foundations of quantum is how does quantum mechanics evolve when you increase the system size, and not just system size for the sake of making it bigger, but as you put more particles, all of them interacting with each other. And this is something that happens in solid state all the time. We have a lot of experience with this that lies at the heart of the condensed matter physics community. It happens in high temperature superconductors or unconventional superconductors, which are a classic example, but more modern. It happens on fractional Chern insulators or systems with non-abelian quantum statistics. And sometimes people say, well, yes, 10 to the 23 particles is a lot of particles. It's a mess. But a lot of these properties emerge already at, when you have 100 particles, 1,000 particles. That's still many, many orders of magnitude beyond what any classical computer can calculate, but it's within the realm of what quantum simulators are going to be able to simulate in the next few years, maybe decade, depending on the number of particles. So I think that is going to be an area which is going to be tremendously interesting to see these emergent properties of strongly interacting matter, many particles interacting with each other, see them emerge as we move quantum simulations of ever-increasing number of particles at relatively reduced numbers, just a few hundred.
Okay, I wanted to talk about what each of you see as the foundational questions, the foundational unanswered questions of quantum mechanics. And we'll just leave quantum gravity to the side. Daniel took care of that. He just needs 100,000 qubits and that'll all be worked out. So, we have this theory that is pretty simple. We know how to do calculations. We're working on interpretation. You all have different platforms. What are the near-term kind of unanswered questions that we haven't touched upon so far? And Wenji, you want to start?
Well, I'm just going to go back to what we just talked about, which is, I think, the problem of scaling to larger systems. I think larger systems out of equilibrium being out of equilibrium is just a generally hard problem. Mm-hmm. And it's even harder when you're talking about a quantum system. And when you add just even a few hundred units together that are strongly interacting, that are way out of equilibrium, we just don't know what to do with that.
Do you have a specific system you're interested in?
Well, a lot of systems that we use in our experiments we create them out of equilibrium and we try to watch them change. We do experiments and we don't understand what we get, right? But we report on it, and we have some simple models that try to explain it, but we know these simple models aren't really working. And so we need better models, and these better models are going to be based on these ideas of large out of equilibrium.
So model is, in this case, a heuristic built on a quantum mechanical framework.
Yeah.
But not something that you could rigorously construct from quantum mechanics.
Well, ultimately, it's going to be built from the bottom up, but you're going to have to learn something about how things interact when you get big, so you can make the right approximations.
Okay. Wolfgang?
Well, Peter, when you asked for fundamental question in quantum mechanics, the first way I wanted to react is there are lots of people who say nobody understands quantum mechanics. It's fun. The quantum measurement process is not understood and all that. And I usually take very clear position. I would say you really have to distinguish between the physics of quantum mechanics and the philosophy of quantum mechanics. And I've been on panels with people who say quantum mechanics is not understood, and I just said, I do understand quantum mechanics. I do quantum mechanics every single day, and I'm in control what I'm doing, and I know what I'm doing. And even in a world of quantum research and quantum technologies, I think it's really dangerous if physicists would say we don't understand quantum mechanics, because that would elevate a theory of science which is testable, where we make hypotheses, we falsify things, which is very rational, on the level of speculation and other things. And especially currently, where science is not always used as a guidance in everyday's world and in politics, I think it is important to emphasize, in science we have clear rules, we have testable hypotheses and all that, and there is nothing mysterious and nothing speculative about quantum mechanics. Maybe if you press me harder, I would say, okay, there are some speculations about what happens when you have macroscopic superposition state. Is there something at the macroscopic scale which affects coherence? That's a scientific question, but it doesn't mean that the quantum mechanics we are doing, that this is fully understood and fully controlled.
Yeah, I tend to agree. Our colleague David Kaiser has written actually a couple of essays about how the understanding pendulum has swung back and forth between, you know, the more philosophical discussions that you allude to and the predictability of the theory, which he refers to as the shut up and calculate regime, whereas you know the rules, you know how to do the calculation, you can make predictions, and because this is all built experimentally.
So anyway, I think it's important also in the context of a quantum initiative at MIT that quantum mechanics is absolute scientific, it's proven, it is the most seriously tested theory in the world, and it has passed all tests and all that. We know what we are doing. We are not speculating.
You heard it here first.
Okay.
Pierre.
So first, I want to second everything that Wolfgang just said. Quantum mechanics doesn't really have any mystery at its foundation. However, what I have observed is that when you take quantum mechanics and you apply it to some well-understood theory, the well-understood theory suddenly becomes no longer well understood. For example, the theory of computation. Computer scientists thought they really understood it. And then, we found that quantum computers could factor larger numbers. And this disproved something that a lot of computer scientists really believed at a very fundamental level, which was the strong Church-Turing thesis, which basically says that anything that can be computed, a Turing machine can compute without taking too much longer. And this is no longer true. And another thing is information theory. Information theory deals with, how to transmit messages over noisy channels. And one of the theorems of information theory says if you have two channels, and this one has capacity C1, and this one has capacity C2, then when you put them together, you add their capacities. Now, this is not true with quantum mechanical channels. And similarly, feedback does not increase the capacity of a classical channel, but it can increase the capacity of a quantum channel. So what I'd like to ask is, are there more theories which quantum mechanics completely changes when you introduce it?
Okay, that's a great answer. Pablo?
So, I already mentioned before, and Monji also elaborated on the fact that I think a key area is the area of emergence as you put many particles interacting strongly together. I think that an even higher level sort of frontier is when you start moving into biology and, from physics into chemistry, quantum chemistry, and from there into quantum biology, which is a subject and I think because as far as we know, the rules of the world are the rules of quantum mechanics. Everything, including us, we're quantum mechanical objects. But it's very hard to wrap your head about, when you look at the basic things that quantum mechanics tells you and the basic things that we experience, right? So I think that when people say that, we don't understand quantum mechanics, they mostly refer to the fact that quantum mechanics is very counterintuitive when you try to apply its principles to macroscopic, objects, day life, experiences, etc. But of course, we're pretty sure that quantum mechanics is, the theory of nature that governs everything, including the behavior of chemistry and therefore also biology. So I think that making that connection, slowly from, a whole bunch of particles together, 100 particles, to then, a more complex, chemical object, to a more complex biological object, to, full-size, humans, that's going to take a long time to understand. But it's something which I think slowly, as we understand better the properties of, many quantum particles interacting together, will make progress. And I think that is also going to be very interesting to look at.
I think it'd be very exciting. So I have one more question, but I wanted to check to see if there are questions from the audience, because I want to be sure we.
So your last question, Peter, was actually answered in terms of unresolved questions on foundations of quantum mechanics. An anonymous question: how much of the next decade's progress do you expect to come from theoretical breakthroughs versus advances in materials, fabrications, and measurement?
I think it depends on whether we get Daniel is 100,000 qubits. So theory or experiment, what's going to drive us forward?
The majority of discoveries are made experimentally because nature is more creative than we are. And if we follow, sometimes if we watch nature, we get better ideas than when we just try to scribble equations. But on the other hand, a certain fraction of discoveries were made theoretically. I don't know, what's the ratio? 80-20? If you look in the history of science.
1 to 4 or so, yeah, in favor of experiment. Yeah.
Yeah, well, I'm an experimentalist, so I agree to a large extent to what. But on the other hand, we work closely with theorists, and what drives our experiments is gaining intuition that the theorists give us onto what to do next, which will then drive the next discovery, and then the theorists help us to explain these things, and so it's a partnership. Yeah. So I think it's not really a fair question to say it's going to be one or the other. I think it's a partnership.
Peter, as a mathematician?
Okay, well, I'll answer as a computer scientist.
Okay.
If you look at the history of computing, lots of algorithms were invented by theorists, and then engineers went out and programmed them up and applied them. But there were also lots of algorithms that were discovered by experiment. And sometimes these algorithms, the experimenters showed that they worked, and the theorists took decades to actually prove that they worked. So you really need both theory and experiment. I mean, if you have just experiment, you don't know what to try. I mean, you try things at random, and most of them are not going to work. You need some theory to give you guidance as to what to try. But of course, theory doesn't always tell you exactly what to try, and it doesn't tell you what you're going to get when you try it. And so you need both.
So I'll just mention, there's an unsung hero here at MIT, Thomas Kuhn, who wrote The Structure of Scientific Revolution, which I think all four of you have faithfully recapitulated about the interplay between theory and experiment. Are there more questions?
One last question. Quantum biology is an interesting idea. What does that mean?
I'll throw it open to anyone who wants to walk the plank.
Well, it's very difficult to imagine that there are coherent quantum superposition states in aqueous solution. So to the best of my knowledge, quantum biology means that certain processes in biological molecules have a phase or a moment of time where they are quantum mechanically. For instance, the initial process of photosynthesis, when sunlight is absorbed and an electron is released, involves really very interesting quantum mechanics. But eventually, the bulk of biological processes is classical. But there are quantum aspects, and some people are studying them.
Anyone else?
Well,
Go ahead.
I agree with Wolfgang that that's usually the context in which it's been mentioned most. Instances where quantum mechanics plays a key role, but then evolution. But of course, the whole thing is quantum, and the question is that, fuzzy boundary between what we call quantum and what is quantum, what we call classical, where that is. And the more we scrutinize and the more we do experiments, that fuzzy boundary keeps moving because we realize we're more sensitive to measure and to understand things where quantum mechanics maybe plays a smaller role, not that big initial role, but they plays a smaller role. But this is a constantly moving target as we are able to do more precise experiments with at what level, because we know that everything is quantum. Classical is just quantum. We just call it classical because, behaves the way, we understood it before quantum mechanics was
You can set h bar
developed.
equal to 0. That's,
Yeah. So I'd like to say that I think it's very likely that there are a lot of fundamentally quantum processes in biology that have not been discovered simply because biologists don't think to look for complicated quantum effects in biology. And probably most processes in biology do not involve quantum, but evolution is really very clever, and it will figure out how to use quantum to help drive the things that it wants to do. So I think there's probably a lot of quantum processes in biology that haven't been discovered.
Maybe add one more thing, which over the past couple of years, maybe 3-4 years, has been also a lot in the news. Maybe some of you have seen. In terms of the origin of light, for example, there are a whole bunch of scientists that believe that quantum mechanics, in various ways, may have played an important role. Because there you're talking again, now it's very small things. How did they, how were they put together? What were the initial chemical reactions, the initial selection of chirality of certain things, that enabled, putting together life. And that's, origin of life is life in small forms, right? Not full-size humans. So there also, for example, a lot of people have been talking about quantum and biology.
I'll give the last word to Munji if you want it.
So, I agree with everything that's been said. The molecules are intrinsically quantum mechanical. You put a bunch of them together, eventually get a human. So we're intrinsically quantum mechanical. But I also, would agree with Wolfgang. If you take a process that's fast enough, it's going to be quantum mechanical in biology. We see, because we get photons that are quantum mechanical objects, we can see single photons with our eyes. That's kind of amazing, right? And that's a quantum mechanical sensor that we have there in the back of our eye. And then that gets translated into a nerve signal. That process is a little interesting also. So there's probably, as Peter said, there's probably a lot of quantum mechanical sensing that we do that we're not even really aware of. And so I think we're scratching the surface on understanding how quantum mechanics and biology really interact with each other. And so I look forward to to hear more about these things.
Yeah, I was actually quite interested by the experiments, with the xenon, different isotopes putting fruit fly. I'm going to go home and try that. Maybe on my cat. I don't know. No, I wouldn't do that. Okay, we have no more
questions.
We do have a couple of minutes if there's I'll take one question from the audience. Otherwise, I'd like to thank the panel. It was a great discussion. And thank Dana for organizing this, and Ian, and close this session. Thank you.